Hi, this is Justin Crooks, AI7SG. Some of you were requesting a more detailed explanation of how the Pico2 generates the amplitude and phase waveforms for polar modulation, so I threw this together. The QRO20 uses the Pico2 for its polar modulation. The PC itself, PC or laptop, actually splits it into a phase and amplitude. So the IQ data from the single sideband CE-SSB algorithm gets converted to a phase and amplitude on the PC because it has a few more resources than the Pico2. For the phase path, the first step is we are going to round it to a 10-bit value, which will then get upsampled using a FIR filter, interpolated, sent to a lookup table, and then to the HSTX port on the Pico2. For the amplitude path, again on the PC, we're going to convert it to amplitude. We're going to round it to the value that represents full scale on the Pico2 at that frequency. More on that later. Then that's going to get upsampled, interpolated, and then sent to the PWM output, which will then be filtered. So as I said, the PC laptop converts single sideband IQ data to magnitude and phase. If we look at an example here, let's say 14.336 megahertz to make it easy. The magnitude and phase data would get sent at 56 kilosamples per second, but this is going to vary by frequency because we do this exact division. The phase data is going to get upsampled using a FIR filter to prevent any extra frequencies popping up in the spectrum using an 11-tap half-band filter. This only uses 2 multiplies per sample, which is super convenient for the low resources of a microcontroller. The other thing to note here is we take advantage of the fact that there's only 3 kilohertz worth of spectrum in this 56 kilosample per second stream. So it lets us do some tricks like this. We're going to continue upsampling using linear interpolation once it's at a high enough sample rate that it no longer matters whether it's FIR or linear. And then the final trick is we're going to send 64 samples using a single 32-bit DMA transfer. Now this is the trick that actually got me excited enough to make the hardware. The Pico2's HSTX port, which is the double the clock rate. So if you're running at, say, 150 megahertz clock, this can actually output at up to 300 megabytes per second. It's kind of incredible. But we're not going to run it quite that fast. We're just going to run it at exactly 4 times the RF frequency. So it repeats every 4 samples, and this is super handy because there's a trick in this HSTX port that lets you, if it's exactly 4 samples long, you can repeat it multiple times without even touching the DMA. It'll just automatically do it based on your settings. After that, it's going to go to the HSTX port and then to an R2R DAC. That's basically just a couple of resistor packs. It's not the most linear way to do a digital to analog conversion, but for 8 bits, it's going to be just fine. And it turns out that 8 bits is still plenty of resolution to get, typically 48 to 50 dB, especially if you use 1% resistors. And worst comes to worst, you can always do some linearization in software. The output from that gets amplified, and it can be output to the antenna tuner because it's also a convenient frequency for that circuit. But typically during transmission, it's going to go to a comparator to drive our LMG1210 GAN FET driver, which will then drive the GAN FETs, which will then go to the antenna tuner and then to the antenna. For the amplitude side, the data is going to come from the Pico2, and we're basically going to, the amplitude data comes from the pulse width modulated output running at 150 megasamples per second. For the 14.336 megahertz example we're using, the PWM would be set to a period of 167, which is the nearest value to that frequency that works for this architecture. That works out to about 1.113 microseconds, which is as close as we can get to 1/16th of the RF frequency. Each upsampled value, for example, you notice that we had up to like 336 in the example. Let's say it's 251. We're actually going to divide that into two values, two samples that are that add to the 251 and are as close as possible. This is going to reduce the filter requirements on that PWM signal before it goes to our GAN switching regulator system. Occasionally a value has to play once or 3 times as needed to keep the phase and amplitude aligned, but fortunately their DMA transfers are set up to kind of automatically handle this, which is pretty handy. I mentioned that phase table earlier. Here's what it actually looks like. It's going to be 1024 values, and basically I actually wrote a little script in C to generate this for me so I wouldn't have to type everything in. So these are the actual values that are going to get written to that 32-bit register, and then if we pick one, let's just go to the top here. We have a hex 80, which is basically mid-scale, 02, which is about max negative, 80, which is back to mid-scale basically, and then FE, which is basically max positive. And then you can see the phase slowly rotates through that phase table sample. Okay, now let's look at the process PWM function. This is going to turn our low rate pulse width modulated values from the PC into a high rate value to actually drive the PWM circuit on the Pico2. Basically what we're going to do is we're going to do a little mem copies and upsampling. Here we are. This is essentially that first fur filter. You can see the 2 multiplies I mentioned. This ends up being an 11 tap fur with as little math as I could squeeze in. There might be a better way to do it, but I think this is about as close as I could get. And then of course we've doubled the number of samples, so then we have to run the next fur filter over over twice as many samples. And then finally we get into the linear interpolation area. Again, I tried to make the math as efficient as I possibly could, and now we've upsampled by a factor of 4, and essentially we're just going to copy that into the output array using the phase table pointers. The poorly named process fir code is actually for the phase information. It is possible that our phase is going to wrap, and we really don't want anything to wrap during our interpolation. So here's some code to safely unwrap that in the event that it happens. Some more mem copies, some more fur filter upsamples. You probably recognize this fur filter. And then, of course, after it gets upsampled, it does go into I believe there's a linear section. I don't see exactly where that is. Now let's look at how to set up the Pico2 hardware to generate these PWM and phase outputs. This is our core 1 entry. I'm using the second core to drive just the PWM and the phase output. That leaves all of the other functions for the first core, including a USB and all the command processing, etc. So of course we're going to have to set up the PWM circuit. You can see here we're wrapping at some number of clocks, and that's going to depend on the actual output frequency. And we are inverting our output because the LTC7891 circuit that I designed actually has the lowest output voltage for the highest DAC, I guess, PWM output. So we just invert it. We're going to enable it, and we're going to set up some DMA channels for it. That way code doesn't have to run to refill that PWM circuit. It all happens automatically behind the scenes. We're also going to have to set up some the HSTX port. You can see there's some hardware registers that have to be written, and some of this you can see we're setting particular register settings so that it repeats automatically up to, I think, exactly 16 times, so that there's very few actual DMA writes that have to occur. It's a very lightweight. But we still have to set up the DMA channels in a ping-pong sort of fashion. We're going to essentially point to these phase table pointers are going to be what we use to actually load the HSTX DMA or FIFO buffer. There's more documentation if you look through the RP2350 manual. This will probably all make more sense. We're configuring it for 64 samples, and then to automatically wrap on those 64 samples using the DMA and the fast writes. That's plenty large enough for us. And then of course we have to set up the second one as well, configure everything, and then start both the PWM and the HSTX DMA channels.